In this lecture, we are going to discuss the unit cell. So this is going to be the smallest component of our or of our crystalline structure. So, sorry. um, so a crystal lattice is what forms when we let material cool and form a crystal very slowly. So as if crystal, and it might not necessarily be a temperature change, but a concentration change. But if we allow a solid to form over a long period of time, then the particles that are going to go from the liquid to the solid state will be able to arrange themselves such that they're maximizing the intermolecular forces that attract them to one another. And so that's how we form that crystalline solid, is the atom having enough time to kind of maximize its location in the solid structure to overall decrease the potential energy of it. And so when we have a crystalline solid form, we call that arrangement of the particles relative to each other a crystal lattice. The atoms are going to be held in a lattice style structure, like within a very uniform pattern. And the smallest unit within that crystal lattice is going to be called the unit cell. And so this is the foundational building block of the entire crystal structure. So I think of it as a little one by one Lego. You can make other Lego pieces from that one by one, but it's kind of the foundational brick that you have when you're building any sort of Lego structure. So here's an image to help us with this. So what I have here is a crystal lattice, and we're representing the atom centers with these little black dots. What the atom is actually doing in this structure, though, is it's taking up more space than that. So an atom might actually be this whole green circle here. And the center of it is the black dot. And those we're also going to call lattice points. So that lattice point is really going to be, in a lot of the simple crystalline solids, a atom's nucleus. And we're going to keep our treatment of crystalline structures a little bit simple. And so lattice points will be that nuclei. And so we're going to have tons of these atoms lined up and arranged in this uniform pattern like we show here. And so each of these black dots would represent the center of an atom. And if we look at what is the smallest repeating unit within that larger structure, that's going to be our unit cell. So here's an example of our unit cell kind of brought out larger. And again, each of these black dots is going to represent an atom. And so using a different color for contrast, the yellow is not a very good contrast color, we would have two atoms that were approaching each other and touching essentially and arranging themselves so they're packed in right next to each other, taking up that volume. So we have a few terms here. So that lattice point is going to be any of these points of the lattice that are typically going to be the centers of the atom. And then any plane where these points are connected, so I'm going to highlight a plane in our larger structure right here. That's going to be a lattice plane. So it's just saying it's like a plane within that structure. And so within this larger piece that's shown right here on the right, we can see we have a lattice plane here, and then there's another plane in the middle and another plane on the bottom. You could also think of these planes as being on the sides here. Here's a lattice plane, and then there's another in the middle, and then another at the end here. So all chemists who are inorganic chemists love MC Escher. And if you've been in my office, not that any of you are going to be in my office this quarter, I've got one of MC Escher's like drawings that it falls into different images all along the top of my office. And if you were coming to get help with this, we would point at it and we would find some unit cells in the MC Escher picture. But so we're going to do it here only. You can always look up MC Escher images online and try to find the unit cells within them. So here's one with ducks, and they're alternating colors, white and black, so you can actually see them. And the beautiful thing about these MC Escher drawings is that he takes a unit and repeats it and creates the image with it. And so you can create this entire image with just creating one of these little ducks that you can then put right next to each other and create it. And so when you look at this on kind of a larger scale, you can try to find what is that smallest repeating unit. And what my eye is always immediately drawn to is one of the ducks. I'm like, oh, well, that's my repeating unit right there, is just one of these little ducks. Because that's how I would create this image most likely if I was doing this as an art project. So I would draw one of those, I would cut it out, and then I would repeat it. But thinking about this as lattice points, I would call like the lattice points here are kind of tricky. You're like, there's the tip of the beak, but like, where's the real point on the edge? Here is the tail is easier. But we want to have just 4 points. Like we want to find a square, so that way we have an easy unit to repeat. And so in looking at that, we can see another one that the eye is easily drawn to is to go from the beak to the center here of one duck to the tail of another up to the tail of another. And within this unit cell right here, we can see that we have two entire ducks within it and some pieces of other ones. And so this is a repeatable unit within our image, but it's not a unit cell. It's not a unit cell because I can make it smaller. And the orange one right here shows that. So this orange unit cell right here is our actual unit cell. And you can see that within it, there's only one of each duck represented. I've got a body of each and a tail of each, and they're not connected to one another. They're actually of different ducks, but that unit itself is the smallest square that I can use to repeat over and over and over and create this image. And so that would be my unit cell here. Here's some different types of unit cells that you'll see in chemistry. And we're not going to get into all of these. That's for a different class. But we're going to focus on things like the cubic cell right here. And we'll talk a bit about a hexagonal scale unit cell as well. And so thinking about these repeatable units, our atoms, especially because as ions are going to be different sizes, or even if they're just atoms, if we have a combination of atoms, we might be making a material where our components, our building blocks, our Legos are very different sizes. And so we don't always get a perfect cubic unit cell. Instead, we'll get rhombohedral or triclinic or monoclinic or orthorhombic or tetragonal. And they all have just different properties about the length versus the width versus the height of that unit cell. And that's how they're defined. So our cubic ones will be nice because the 3 length, height, width, or ABC are all going to be the same. And our angles on it will be 90 degrees. In our hexagonal ones, our length and width will be the same, but our height will be different. And we'll have some 90-degree angles, but then we'll also have one face that's at 120 degrees to create that hexagon shape. So I'd like to throw a few more definitions and a little bit of terminology at you before we actually dive into looking at some of these structures. So I'll start with coordination number. Coordination number is going to be the number of other particles that come in contact with one particle. So you'll focus on one particle and say, how many things touch it? So if I have a really simple structure of just atoms packed next to each other like this, and I focus on one of them, I'll shade it in here. And I ask how many atoms are touching that one atom. That would be my coordination number. So here, my coordination number, I have 4 that are touching it. 1, 2, 3, 4. The ones in the corners that I didn't highlight yellow, those aren't actually touching the shaded in atom at all. They're surrounding it, but they're not actually in contact with it. And that contact is where we're creating the intermolecular force attraction between those 2 atoms. So I've got 4, and that's in one lattice plane. And then I'm going to have a layer of atoms above it and a layer of atoms below that. And in that layer above and below it, it's only going to touch the ones that are directly up against it rather than the ones that are at diagonal. And so there's going to be one above it and one below it. And so I'll have +1 from the plane above and 1 from the plane below. So for this, I would have a coordination number of 6. I would have 6 atoms that are touching it. And for each of our unit cells that we look at in this class, we'll evaluate that coordination number. And when we have a higher coordination number, when we have more atoms touching any one given atom, then we're going to have stronger forces holding that crystal lattice together. So it would be harder to break it apart. It'll be a stronger crystal lattice. It also will increase the density of it. The more atoms that can touch that atom, the closer those all are together. And so we'll also see another factor increase as well, and that's its packing efficiency, which is just how much stuff did you cram into a certain amount of space. So if you enjoy packing moving vans and games like Jenga, packing efficiency is what you are good at, right? And so being able to pack a van very efficiently is the same thing that nature is doing as these crystalline solids are forming. And the more units, more atoms that you can get into the unit cell or touching one atom, the higher your efficiency. And that's going to be equal to the volume that the atoms in the unit cell take up, divided by the actual volume of that unit cell, times 100. So as we see that coordination number increase, we'll see that packing efficiency increase as well. All right, we'll go through some examples of different unit cells in the next lecture.